Hello, everyone. Welcome to HML Mathematics channel. Today, we are going to talk about controllability of a coupled string with control applied at a coupled point. This paper was encouraged by J.P. Ma's 2D case. The paper posted in 1998 in Saitama Mathematical Journal. In Ma's paper, it discussed exact controllability of a coupled vibrating membrane system. Following that 2D case, we discussed the controllability to the 1D case, which is a coupled string with control applied at a coupled point. We will see what's the difference between 1D case and the 2D case. Also, this paper is a very good teaching course for the students who are interested in controllability and partial differential equations, because it provides a comprehensive explanation of all the equations discussed and appeared in the paper. It is a self-teaching material. Let's start. Introduction to the paper. This paper studies the exact controllability of a system of two coupled vibrating strings, where the control is applied at the point in which the strings are connected. The problem falls under the broad field of distributed parameter control theory, which deals with the controllability of partial differential equations governing wave-like phenomena. Controllability is a fundamental concept in control theory, determining whether a dynamical system can be steered from any initial state to a desired target state using an appropriate control input. For PDEs, particularly wave equations, controllability has been extensively studied due to its applications in structural engineering, acoustics, and flexible structures. For example, bridges, membranes, and robotic arms. A key challenge in such systems is the presence of coupling conditions, where multiple wave equations interact at a junction point. The controllability of coupled systems differs significantly from that of a single string or beam because the coupling introduces additional constraints and wave propagation effects. This paper addresses the case where control is applied directly at the coupling point, a scenario that arises in particular applications where actuators are placed at structure joints. The mathematical formulation used in these systems consists of two strings governed by the wave equations, as you see from here. Boundary condition is here. Coupling condition at x equals c, which is between 0 and 1. A control function is acted here with this condition. So the main question is, given any initial displacement and velocity, does there exist a control ft that drives the system to rise in finite time t? Key contributions of this paper provide functional framework which indicates the problem is analyzed in a Hilbert space setting. They created the operator A related to the second derivative with coupling conditions. And this operator A will be self-adjoint, positive, and with compact resolvent. The paper provides very detailed certification to which indicate the Y operator A is self-adjoint, positive, or with compact resolvent. The solution space is decomposed using Eiffel function expansions, allowing Fourier-based techniques for controllability. Exact controllability result of this paper showing the system is exactly controllable if the coupling point C is an irrational number with bounded continued fraction coefficients. In this paper, they set up a set E, which we will discuss later, provide a very detailed explanation. What is the E looks like? The control T satisfies T larger than 2 over I. The IFR relate to strings, density, and the mass. The proof relates on solving a moment problem derived from the Eiffel function expansion and using harmonic analysis to induce the existence of a suitable control Ft. We are going to discuss sharpness of the conditions. The irrationality condition on C induces that the coupling doesn't introduce resonance that prevent controllability. The minimal control time T larger than 2 over alpha is related to the wave propagation speed across the domain. Now let's go to the main part of this paper. Oh, before this, we still discuss some significance and applications of this paper. This work extends classic controllability results for single strings to coupled systems, providing insights into structure control, designing actuators at giants in flexible structures, wave propagation in networks, understanding controllability in interconnected waveguides, numerical math. The spherical approach can be adapted for computational control design. The paper bridges PDE theory, function analysis, and control engineering, offering a rigorous treatment of controllability in coupled wave systems. Future discussions could explore nonlinear couples, damping effects, or multi-dimensional generalizations. After this paper, next we are going to provide some more complicated coupled string or flexible beams to discuss controllability of such systems. Okay, now let's go to see what is system looks like. The system 1 to 4 describes this system. We consider a control problem for a system of coupled vibrating strings. The control function ft is applied at a coupled beam point at x equals c, which connects the two strings. The system is governed by the following coupled wave equations. This equation 1. Omega 1 is times 0t. Omega 1 is 0 to c, and omega 2 is c to 1. So omega 1 is first string, omega 2 is second string. So u1xt, u2xt represent the displacements of the string in omega 1, omega 2, respectively. Alpha is a positive constant related to the tension and mass density of the strings. The boundary conditions are 2. The initial conditions are 3. So the control function applied at 4. So this is the whole system, okay? This page talking about hybrid space setup, this 1D case. We assume that H equals L2 omega 1 plus L2 omega 2 with the inner product defined as this. Omega 1, 2 definition, U1, U2, and U as a united function of two strings. With those definitions, we can consider exact controllability in hybrid space U times V. We are going to discuss what is U and V in next pages, okay? So here we just know U and V are hybrid space with a dense and continuous embedding U belongs to V, included in V. So basically, the controllability problem dealing with for any t larger than 0 and any initial data u0, v0 belong to u times v. For any control f belongs to L20t, whether we can find a solution AUXT of the system such as u and ut belongs to c0t u times v, okay? Then we drive the system to the rest. We still need to define the controllability. Yeah. So next step, we just see, we define the file. The exact controllability, the concept of exact controllability for the system 1 and 2. Definition 1, exact controllability. Let t larger than 0. The system 1 and 2 is called exactly controllable in u times v if for any initial data u0, v0 belong to u times v, that exists control f belongs to f2, 0t, such that the corresponding solution of 1 to 4 satisfy uxt, utxt equals 0 for all x belongs to omega. Then here we define an operator A with domain dA in H as follows. With this definition 6, we will tell you the operator A is positive, self-adjoint, and has a compact resolvability. Its Fn values and Fn functions are given by lambda n 7, and this Fn value, Fn function is 8. Fn functions are orthonormal in H, meaning these are equals delta m, where delta m is the canonical delta. So function Fn function theta n and m is orthonormal in H. The Fn space Zk are defined as that it's a span space which satisfy this 10. By those setting up, we can say dA is closed subset of H2 omega and becomes here to U. See, the U is dA, and the V is dA 1/2. Why we can have, because A is self-adjoint and positive, A has a unique positive square root, A/2, which is dA included, embedded in this space with these characters. So dA A/1/2 becomes here space with the inner product. This inner product for UV. Why do we do this? We can see we are considered the controllability in the function space. Then all here is we trying to set up operator A and give a proof certification. Why dA? The A is positive, self-adjoint, and has a compact resolvability in the Hilbert space. Okay, then you can learn how to do this proof. First, we prove the positivity of A. I do not, for this is the calculation, regular normal calculation, okay? You can practice the calculation by yourself. So this, the conclusion is this, A is positive. Then we are going to prove self-adjointness of A. You can do by yourself with the conclusion. Then we are dealing with a compact resolvent, okay, with the conclusion of that. This is a self-teaching in course. It's very detailed presentation for you to learn how to deal with this problem. Okay, then we can, that's a summary and conclusion, okay? Okay, the proposal actually we are going to find a strict solution for the system 12 to 20, which is equal to system 102. So we're building a new system which can be replaced by system 102, 124, okay? Pay attention to the details, the definition, the setting up. We are going to do matrix operator formulation 15 to 17. Here put the space V times H, defining with the inner product. A new operate analytic A, and this operator analytic A is the infinitesimal generator of a C0 semigroup in V times H. According the semigroup theory, the structure solution of system 6 to 17, that's to 16, 17, okay, system 17 is a system similar to system 10124 is given by this form, okay? This is a summary. Then here is the step-by-step rule why the operator defining in 19 is the infinitesimal generator of a C0 subgroup on the here but V times H, where V is dA 1/2 energy space, H is here but space. Okay, this is a detailed verification or verification set. To show A generates a C0 semigroup, we use Yoshida theorem, which requires closeness of A, dissipativity of A, and range condition. Okay, if they are satisfied, we will see the C0 semigroup. And then we'll use the semigroup theory to obtain the strict solution of the system 6 to 17, which also 12 to 14, which also can be replaced by a system 1 to 4. Okay? So this is the first part. A is closed, densely defined. And this is the second, dissipativity, okay? Conclusion. And this step 3, range condition, okay? So by the theory of the Yoshida, we will all solve this, okay? This is the explanation, physical interpolation of semigroup, okay? Actually just with system 1 to 4, okay? This is summary, okay? Then we will approve a strict solution of system 16 is indeed for the system it indeed have a struct solution to system 6 to 17. Okay. So why F we put in the H4, okay? Because our BF is in H2, okay? So we examine our struct solution. Then we see differentiability of the conclusion, convolution. Then verification of the equations. Then the uniqueness. Last one, uniqueness. Okay. This is the final conclusion. And in this function space. Then we are going to introduce a homogeneous system 21 to 23. Then we, from the uniqueness of the system, we define a weak solution for the system. Then this is a very key equation of 25, okay? Then the range is 26. This is approved. Why is the 25, 26 coming from? A very good practice for you to calculate, especially the ability to do the calculation of the partial integration. Integrated by parts in space, okay? Apply all the conditions from the system 1 to 4. The finally, we see that 26 is indeed match 26 in the paper, okay? This is the explanation of the key equation, okay? Then we have the time to define a mild solution. This is a mild solution for system 1 to 4, okay? Then we will have my lemma 1, okay? Lemma 1. First, we define this. Then we will approve this definition of the weak solution, the existence and uniqueness of the weak solution. This is the explanation of definition 3 and lemma 1, okay? Okay, let's approve lemma 1. Very good practice for your calculations. And use the quality of delta and n. And the function space definition, all this function space, Sobolev space, then you can just review what you learned in the classroom of the function space, functional analysis, okay? Functional analysis, knowledge of functional analysis all here. Are you able to do this part? These are all the definitions. This part is very well practiced for functional analysis to see your ability. This definition. Here is the application to the W1. Okay, why use W1? Okay, the purpose of use W1 is try to use these theorem. Okay, define a linear functional, then use this part. Use the purpose is to use these representation theorem. Okay. Okay, let's do again slowly. Lemma 1. Step 1, define the space and operator. Step 2, establish the chain of embeddings. Step 3, define the linear functional. Step 4, show this functional is bound on this space. Step 5, use the solution map. Step 6, express the left side and hand side using W1. Step 7, apply the least representation theorem. Step 8, construct the Miller solution. Then, once we accept all the solution, right? We are going to expansion to obtain the control FT. Because the purpose target for us is to find the FT belong to L20T. Then we expand the control FT in terms of F functions, theta and S. Okay, expansion of delta E0x V0x. Then we reduce it to find some movement problem, okay? To try to, in order to find the FT, we try to solve some movement problem, like 32. This is a double movement problem for each M, okay? This is the movement problem part. This introduce a set E. Then we will have a CM exact controllability. Let C belongs to E, where E is a set of irrational numbers in 0, 1, which bound the continuous fraction coefficients. Assume T larger than 2 over alpha and U0 will belong to U times V. Then the system is exact controllable in U times V. Okay, this is the main The U is dA, the V is dA 1/2. Okay. Then the proof of the theorem. Okay. This is similar. Okay. And we talk a little about the definition of the set E. What's the E looks like? Okay. These are examples of set E. Why is met? Then we provide a numerical example to show why theorem 1 is existing. Okay, this is an exact case example. Okay. So in this example, what is ft looks like? Ft. So if it's really at t equals 3, u x 3 equals 0. Okay, almost. There's the expansion why it is work. The self-teaching course. Then we'll discuss, after this, we'll discuss some further open questions, okay? To see whether we can deduce some conditions when you establish the function space. Then if is there any possibility to give an or weakening the spaces, okay? Relaxing your dA, okay? So actually, V equal is the minimum of the energy method, okay? Next time we may consider the controllability in H1 times L2. We may consider it, okay? So here is why weakening fails, okay? Whether we really can find a different FT. Because we dealing with the x equals c in between 0 to 1, not on the x equals 0 and x equals 1. This is a 2D case, okay? This is a reference. For the string part, only in Japan in 1995, they discuss the exact same system. he discussed approximate controllability of capital member system with Cooper. Okay, so we following his work. We discuss exact controllability for 2D. And today we use discuss the 1D case. Okay, but we still haven't discussed the approximate controllability of 2D case. And if you, we may find some time to deal with it. Okay. And here, next time we discuss this one first. This one is flexible beams. More a little bit complicated situation and close to real situation. Okay, this paper deal with both approximate controllability and exact controllability. Okay. Okay. Thank you, everyone. Until next time.